Today we're here to witness the factory acceptance test of the RNDE system for the rocket processing.
The RNDE brings state-of-the-art X-ray technology to bear to assist the Army with its mission of safely and efficiently destroying the chemical weapons.
This is a new component to our rocket line processing. This is a way for us to scan aged rockets that we have in the inventory to determine if they're leaking either internally or into the shipping and firing tube. Early identification of the leakers, the key benefit is if we identify them, we don't send them into the process, we don't contaminate a clean area. If we contaminate a clean area, we'll have to stop processing to go in and perform decontamination operations to get all those readings back down to near zero so we can continue to process again.
In an effort to provide context to the Rocket Non-Destructive Examination System, or RNDE, we will start this video with a high-level view of the M55 rocket line at BG Cap. The M55 rocket lines consist of 4 primary processing rooms: the unpack area, explosive containment vestibules, explosive containment rooms, and the energetics batch hydrolyzer room. The RNDE processing will take place in the unpack area, where pallets of M55 rockets will be delivered from their storage igloos via enhanced on-site containers, or EOCs, into the facility. The pallets will then be removed from the EOC and depalletized as they are prepared for the non-destructive examination system. The primary function of the RNDE system is to safely and efficiently examine the contents of a M55 rocket contained in its original shipping and firing tube prior to processing the unit on the rocket line. The inspection process will allow trained operators to identify M55 rocket assemblies that may have leaked from their agent cavity into other parts of the rocket during their 60+ years of storage. Once the RNDE inspection and review has occurred, passing units will then be transferred to Line 1 or Line 2 input conveyors to begin the demilitarization process through the vertical rocket cutting machines in the ECV rooms, followed by the rocket warhead containerization system in the ECR and EBH rooms. The RNDE system is a custom, state-of-the-art, non-destructive examination system. The RNDE is a self-contained, standalone system that contains 2 independent work cells enclosed by polycarbonate perimeter safety standoff guarding to support time, distance, and shielding to the operators. The RNDE system utilizes fully automated material handling coupled with an advanced X-ray system with a direct conversion detector array to accomplish the non-destructive examination of the M55 rocket assemblies contained in their shipping and firing tubes. This system was designed and built through a collaborative effort to produce a safe and efficient processing environment. Each of the RNDE work cells contains the following: an input and output transport cart, an X-ray scanner and detector housed in a leaded enclosure, a 2-axis pick-and-place robot for material handling, a servo motion sled with tilting mechanism, safety interlocks, and an operator cart control panel. A factory acceptance test, or FAT, for the Rocket Non-Destructive Examination System was held on February 24, 2021 at CRG Automation in Louisville, Kentucky. The testing was conducted in an area of the factory that replicated the size of the unpack area room at BG Cap, so that material movements outside of the RNDE system could be demonstrated. As previously mentioned, to start the RNDE process, pallets of M55 rockets contained in their shipping and firing tubes are delivered to the UPA and unloaded from the enhanced on-site containers, or EOCs. Once a pallet has been removed from the EOC, it will be loaded onto an unloading table. UPA operators will then remove and store the pallet dunnage in preparation for depalletizing the SFTs. The unloading table can be height adjusted to ensure the operators are able to transfer the SFTs to a waiting input cart in a safe, ergonomically, and efficient manner. Once the table has been adjusted to the proper height, the operators will mark the top of the SFTs at the 12 o'clock position to provide a visual reference of the original SFT storage orientation. The operators will use the visual reference while transferring the SFTs onto the input cart, taking care to keep the 12 o'clock position as close to the original position as possible to minimize any disturbance to the liquid contents. Once the white input cart has been loaded with up to 5 SFTs, the operator will move the cart to the RNDE input cell opening and insert it fully to the hard stop. Next, an empty green output cart will be inserted fully into its output position. The operator will then press and hold the reset button at the operator cart control panel that will automatically lock the carts into their positions, enable all safety interlocks, and initiate the auto sequence start of the RNDE system. The RNDE process begins with the 2-axis pick-and-place robot picking the first SFT from the input cart. Once picked from the input cart, the robot will then place the SFT on the servo-driven motion sled. A pneumatically controlled in-stop will then push the SFT to a set position, and the motion sled will be tilted to an operator preset angle. The purpose of the induced angle is to enhance the visualization of liquid contained in the SFT or M55 rocket assembly by utilizing gravity. A beacon siren will audibly alert operators in the area once the X-ray device has been turned on at the start of the first scan. Additionally, the RNDE control operator will have a human-machine interface, or HMI, that will indicate all system activities, statuses, and alarms so they can monitor the cycle progress. Once the motion sled has tilted to the preset angle, the servo drive will engage and move the loaded SFT into the X-ray cabinet. The speed at which the SFT is moved across the X-ray beam is precisely controlled to ensure excellent image quality. The SFT motion sled will come to a stop once the full M56 warhead contained inside the SFT has passed through the X-ray beam. This results in an X-ray image from the front of the SFT's end cap down to the M56 warhead connection to the rocket motor's foreclosure, encompassing all known potential leak locations. Upon completion of the X-ray scan, the resultant X-ray image will automatically appear on the Image Review and Disposition System Monitor, or IRDS. Each RNDE cell has its own IRDS monitor. The trained operator will then review the X-ray image, looking for any chemical agent that may have leaked during the 60+ years of storage and would be problematic for downstream processing. Upon review of the image, the operator will take one of the following 3 actions: pass the unit, rescan the unit, or fail the unit. If the unit is passed, the 2-axis robot will pick the SFT from the motion sled and move it to the output cart. Only passing SFTs will be placed on the output cart. If the operator would like to conduct additional image diagnostics, they can rescan the unit and alter the tilt angle of the motion sled. By altering the angle of the rescan, the operator can gain additional insights by monitoring the liquid levels in the X-ray image and comparing against the previous scan. The operator can conduct the rescan operation as many times as necessary to ensure accurate image diagnostics. If the unit is failed, the 2-axis robot will pick the SFT from the motion sled and move it back to the input cart. Only failed SFTs will be placed back on the input cart. At the completion of cycling 5 SFTs through an RNDE cell, the system will automatically stop and release the locks on the input and output carts. The UPA operators will then remove the carts and carry out their standard operating procedures. The output carts will be moved to transfer the passed SFTs either onto input line 1 or line 2, or they may be repalletized and stored near the lines to be processed at a later time. If the input cart is removed and contains any SFTs, then these units would have been deemed failed, and the UPA operators would commence their overpack operations in accordance with their standard operating procedures. Once the input cart is cleared, it will be taken back to the unloading table, and the operators will load 5 new SFTs in preparation for the next RNDE cycle. The RNDE system has been designed in compliance with Title 21 Code of Federal Regulations, Part 1020.40 for cabinet X-ray systems. Operator safety and system redundancy were paramount in the design and implementation of this custom solution. The Operator Human-Machine Interface, or HMI control, provides an abundance of information to the operator to ensure they can monitor all processes, progress, and status during the automated cycles. The RNDE system has been designed for fail-safe operation, so in the unlikely event a component failure, the system will automatically stop processing and shut down in a safe mode, alerting the RNDE operator to the issue. The RNDE system also contains numerous interlocks that ensure personnel cannot enter the cell during automated processing for their safety. If any one interlock is not satisfied, the system will not operate. Additionally, the RNDE system has several status indicator lights that are viewable from many different angles around the perimeter of the system and will inform any personnel near the system as to the status of the RNDE operation. The RNDE system also contains industry standard e-stops in the unlikely event operations personnel need to stop the system during the automated cycle. Once the e-stops have been cleared, the RNDE will automatically recover from its stop mode. During the FAT, the e-stop was demonstrated in the middle of an active X-ray scan. Once the e-stop was cleared, the system successfully restarted and rescanned the SFT that was in process.
It's going to be a rescan?
That's what we're doing now. Because what happens when you stop it halfway, your image is scanned halfway.
Yep.
As previously mentioned, the RNDE is a standalone system that can be operated independently of the M55 rocket line processing. Because the systems are not interconnected, the RNDE can afford the operations team to scan SFTs well in advance of needing to process them on the main input feed lines. This allows the RNDE to provide a buffer stock of inventory to ensure continuous, uninterrupted operation of the input feed lines. Therefore, cycle times on the RNDE are not critical to main plant operations. However, during the FAT, we conducted a time trial of a single cell cycling 5 SFTs, which demonstrated that the RNDE, with 2 cells in operation, could easily meet and exceed the expected processing needs of the main lines.
Rocket number 5. 14 minutes. And 12 seconds.
I was new to Chem DMIL prior to this project. I've been here about 6 years. The last 2 have been focused on this rocket process redesign, and I honestly could not have asked for a better group of people to accomplish this mission.
This team came together and developed multiple elements for the process, which today, of course, the NDE. Prior to that, we had the rocket warhead containerization system, which took the warhead and containerized the warhead in a canister. We also had the vertical rocket cutting machine, which improves the cutting process, where we separate the warhead and rocket motor. And then again, finally, the NDE is the last piece of the handling system.
I'm retired military, U.S. Army Chemical Corps. I dug weapons out of the ground. I maintained the readiness of the stockpile. When I retired from the military 20 years ago, I began working with DMIL to get rid of these chemical weapons. And the technology that we're using today to get rid of these is, from a safety perspective for the operator, it supports the cardinal rule, minimum amount of people to minimum exposure of the item, be it agent or munition, for the minimum amount of time. The robotics is a big part of that. The technology is fantastic, and from an old Army chemical soldier, this is the path forward to safely dispose of these weapons.